Good morning, everyone.
My name is Trigonometric from Industrial Engineering, batch 2023.
My name is Afifa Zafral Taufik from Industrial Engineering, batch 2023.
And in today's video, we're going to explain about higher derivatives.
And I'm Raditya Bidarma from Metallurgical and Material Engineering, batch of 2023.
And I'm Pramadipta Vasska right now from Meteorological and Materials Engineering, batch of 2023. And today we're going to explain about derivatives of trigonometric functions
and its uses in engineering. So let's enjoy the video.
Okay, so here we got the derivatives of trigonometric functions. First of all, we have the derivative of the function sine x is cosine x, and the derivative function of cosine x is minus sine x, and the derivative function of tan x is secant to the power of 2x, and the derivative function of secant x is secant x times tan x, and the derivative function of cosecant x is minus cosecant x times cotangent x, and finally the derivative function of cotangent x is minus cosecant to the power of 2x. And these derivatives are fundamental for calculus and are used in various applications in mathematics and science. So here is an example. Okay, so here is the an example. Find the derivative of 2 sine x plus 3 cosine x. So as we said before, the derivative of sine x is oh my god. Okay, cut. So here is an example. Find the derivative of 2 sinus x plus 3 cosine x. So as we said before, the derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. So let's rewrite the function real quick. So the sine sine the derivative of sine x is cosine x. So let's just like that, and then the derivative of cosine x. Oh, let's do this again. Oh my god, I can't do this. So here we have an example. Find the derivative of 2 sinus x plus 3 cosine x. So as we said before, the derivative of sine x is cos x, and the derivative of cosine x is minus sine x. So let's write the function again real quick. So we're just going to derive the function. So 2 sine x will become 2 cos x because the cosine is the derivative of sine x. And then 3 cosine x will be minus 3 sine x because the derivative of cosine x is minus sine x. That's why we added the minus there. So it will become 2 cosine x plus minus 3 sine x. And that is the answer for this question.
Of trigonometric derivations in real life would be its applications in simple harmonic motion, one of which is its oscillating in an oscillating spring without damping. So in this diagram, we can see that a mass m, let's say this mass m, is oscillating upwards and downwards when it's attached to a spring. The symbol A here represents its maximum displacement. and it's a graph of this maximum displacement against time. And this graph can be expressed with the function s of t equals to the amplitude, or the maximum displacement, times the cosine of its angular velocity omega times time t. With this information, we can calculate its velocity with regards to time and its acceleration with regards to time, based on the relationship it has with the time position graph. We know from kinematics that the velocity against time graph is the first derivation of the position time graph, which here we can differentiate using the derivation rules. We have the a, we take the derivative of the inside first, which is, since it's respect to t, it's only going to be omega times the negative sign of the inside again, omega time. Here, this would be the equation which we would need to calculate the velocity time graph. Next, to get the acceleration, we can always just input the second derivative of the position time graph, which would be, using the rules again, we have negative a, since it's a constant, we bring it down, omega, times the derivative of the inside again, which would be only omega, so it's omega squared, cosine of omega time. So here's an easy example of a differentiation question with trigonometric functions. So here we have f of x equals the sine cubed of 3 of x plus cos to the power of 4 of 2x squared. So first we would take the differentiation of this and the derivative of this. So first of all, we can apply the chain rule for the sine cubed of 3x. First we take the cubed first, so we take the derivative, which is going to be n times x power n minus 1, which would be 3 times sine of n minus 3 minus 1, which would be 2 times 3x. Next, we will take the derivative of the sine, which would be cosine, of 3x. Then we multiply this by the derivative of 3x, which would be 3. Next, we will take the derivative of the cosine of the second function of cosine to the power 4 of 2x squared. We will do the same thing, so take the derivative of the power first, which would be n. Here is n is 4, so we take 4 cosine of 4 minus 1, which is 3, of 2x squared, multiplied by the derivative of the cosine, which would be negative sine of 2x squared. Next, we take the derivative of the 2x squared, which would be multiplied by 4x. So hence, if we can multiply the like terms, in which case f prime of x would equal to 9 sine squared 3x cosine 3x minus 16x cos cubed of 2x squared sine of 2x squared. So here we have a harder example of differentiating trigonometric functions. We have g of x equals to x cosecant x squared plus 2 plus cosecant of x all divided by 3 minus cosecant x squared plus 2. Here we have the quotient rule because of its rational function, where d over dx equals to d over dx of u over v equals to u prime v minus v prime u divided by v squared. We also have a product rule in x times ca cosecant x squared plus 2, where the derivative of uv, or u times v, is u prime v plus v prime u. With this information, we will let the top function be u and the bottom function be v. Hence, the u prime we can compute as the derivative of x cosecant x squared plus 2 plus cos x, and the derivative of v would be 3 minus cosecant x squared plus 2. Next, we'll find the derivative. So the first part here would we would use the product rule, where u is x and v is cosecant x squared plus 2. So first of all, the derivative of x would be 1, so we just copy the v, which is cosecant x squared plus 2. Next, we take the derivative and we add it with the derivative of cosecant x squared plus 2 multiplied by x, so we have x times the negative cosecant of x squared plus 2 multiplied by tangent x squared plus 2 multiplied by 2x. Finally, we take the derivative of cosecant x, which is negative sine x. Next, for v prime, we take the derivative of 3 minus cosecant x squared plus 2, which is just cosecant x squared plus 2 multiplied by tangent x squared plus 2 multiplied by the inside, which would be 2x. With this given information, we can now compute for g of x, or the derivative of g of x. So first we need to take u prime, which would be cosecant of x squared plus 2 plus x, minus, because it's minus cosecant x squared, so minus cosecant of x squared plus 2 times tangent x squared plus 2 times 2x times x, which would be 2x squared minus sine x. All of this is then multiplied by v, which we know as 3 minus cosecant x squared plus 2. Next, we subtract this entire part with v prime times u, where v prime, which we found as this one here, which would be 2x cosecant of x squared plus 2 multiplied by tangent x squared plus 2. This entire fraction would be multiplied by u here, which would be x cosecant x squared plus 2 plus tangent plus cosine of x, and x cosecant x squared cosecant x squared plus 2 plus cosine of x. This would all then be divided by v squared, which would be all of this entire thing would be divided by v squared, which would be 3 minus cosecant of x squared plus 2 whole squared. Then computing this function, or expanding this function, should give us this function right here, which is very, very long. You can pause the video if you want to see the entire function. Here it is in its entirety.
So what is the definition of a higher order derivatives? Higher order derivatives refers to repeated process of taking derivatives of derivatives. Higher order derivatives are applied to sketch curves, motion problems, and other applications. So this is an example. Now we need to find the first derivative to begin. The derivative of x to the fifth is 5x to the fourth plus the derivative of x cubed is 3x squared minus the derivative of x is 1 plus the derivative of a constant is 0. So 3 times 5, 15x plus 2 times 3, 6x squared minus 6 times 1, 6. Now, we need to differentiate this expression one more time to get the second derivative. Okay. The derivative of x to the fourth is 4x cubed plus 6. The derivative of x squared is 2x minus 0. Because the derivative of a constant is 0. Then 15 times 4, 60 x cubed plus 12x. So this is the second derivative. That's it. So easy, right?
Oh, hello again, everyone. Let me reintroduce myself. My name is Raditya Abhidharma from the Metallurgical and Material Engineering, and I'm going to continue on the explanation under the higher order of derivatives. And this is my part, of course. And to be specific, I'm going to be covering the application of higher order and also answering some easy and hard questions regarding higher order. Now, let's go. So the application of higher order in our calculation here is the calculating of acceleration. So if you follow some class like physics, you will find that the derivative of position function is the velocity and acceleration. The velocity is the first derivative, while the acceleration is the second derivative. Now, what are we applicating this to? It is a speed gun. So what is a speed gun? A speed gun is a tool used to calculate the speed and acceleration of an object. In this case, we are going to calculate cars. It works by noting the position on a car by a time frame, then made it into a position function, by which it needs to be derived in order to find the speed and acceleration. So let's try calculating one. Say a speed gun captures a car speeding. The speed gun snaps the position function within 1 second with the function of ft equals 30t cubic minus 5t squared minus t. Calculate the speed and acceleration of the car when the speed gun captures its position. Now, we can find that the time, or t, equals 1 second, of course. And we can find that the position function, in this case, that is ft, equals 30t cubic minus 5t squared minus t. Now what we are going to do is just derive it first for the velocity function, that is vt. It is equals to f prime t. So we can d over dt everything here. D over dt for 30t cubic minus d over dt for 5t squared minus d over dt for t. Now 30 times 3, that is 90, t 3 minus 1, that is 2, so 90t squared minus 10t minus 1. Since we found this velocity, we can calculate it by v1, so we can replace the t by 1. So it equals 90 times 1 squared minus 10 times 1 minus 1 it equals 79 meters a second. We found it. Now for the acceleration, we can put it into a t equals f double prime t. So it's the higher order of the derivative. We can calculate it by inputting again the velocity function. So d over dt and everything again, 9dt squared minus d over dt 10t minus d over dt for 1. So 180t minus 10, you have found it. So the acceleration a1 can be calculated as 180 times 1 minus 10. It's going to be 170 meters a second. That is the answer. So we know how a speed gun works. Now let's move into an easy question, that is to find second derivative of y equals x to the power of 4 minus x to the power of 3 or cubic plus x squared plus 5. So we can find it by first we can derive it, the first derivation. So I'm not going to d over dx and everything here because you already know how to do it. I'm just going to do 4x cubic, so 4 times 1, minus 9x squared plus 2x. Now we can find the second derivative, that is 12x squared minus 18x plus 2. Since when you are going to derive something, let's say an axn, it's going to be derived as a times n x n minus 1. So you can implement it here. It is the same for both derivative. It's the basic of derivative again. A higher order, it means just there is a second derivative to the first derivative. We're going to move into the hard question. Now we need to find the second derivative of y equals ln for x to the power of 4 minus 20x minus 3. So in old fashion, we're going just to do the ln in 1 over, so we can write this as y prime equals 1 over its original function, so 4x to the power of 4 minus 20x minus 3 times its derived first derivation of its original function, so 16x to the power of 3 minus 20 minus 3. So we can conclude that this is 16x to the power of 3 minus 20 minus 3 over 4. Now we are going to move into the hard question. Find the second derivative of y equals ln for x to the power of 4 minus 20x minus 3. So we can always just ln, what is the derivative of ln? So we can move on y prime equals, so if we found ln, we can do 1 over what is inside ln, that is for x to the power of 4 minus 20x minus 3 times the derivative of what inside of ln, so 16x to the power of 3 minus 20. So we can conclude that the first derivation is 16 to the cubic minus 20 over 4 x to the power of 4 minus 20x minus 3. Now how to find the second derivative? Now since this is a uv, we need to make it into a u prime times v minus u times v prime over v squared. Now we need to find first the u prime, so the u prime is the upper side here. The upper side, it is 48x squared and nothing, because we can always throw 20 out. I'm just going to erase this, and then we can find v prime, that is this bottom part, that is 16x to the power of 3 minus 20. So we can calculate it using this formula right here. So y prime is going to equal 48x squared, and the v, that is underived, so 48x squared, 4x to the power of 4 minus 20x minus 3 minus underived the upper part, 16x to the power of 3 minus 20, times the derived, so 16x to the power of 3 minus 20. You can see here, you can make it to the square later, over 4x to the power of 4 minus 20x minus 3 squared. So we can calculate this into 48x to the squared, 4x to the power of 4 minus 20x minus 3 minus 16x to the power of 3 minus 20 squared over 4x power of 4 minus 20x minus 3 squared. So we found our answer. Yeah, sure, it's not very simple, but I think what makes it a hard question is that it tried to deceive you into not doing the whole because it tried to be so hard. So my tip is that you need to go for it. Just go. There's nothing stopping you from deriving these numbers, of course. And that's all, y'all, about the higher order of derivative. Thank you for listening with me. I hope you have a great time. Peace.
That's all from us. Thank you for watching.
Don't forget to like, comment, and subscribe.
Bye bye.